So, warping space and time, as the subtitle says, science fiction and science fact. We're going to deal with the facts first and then have a quick look at the science fiction before summing up at the end. So, roughly speaking, the contents of this talk can be summarised as a brief history, and that's a very brief history of where black holes stand at the moment. Then we're going to look at the science fact, which is broken into a few different sections, and I'll pause at the end of any section in case there's any questions there. And then we'll finish by looking at science faction and then a quick peek into the future. So firstly, a brief history. Perhaps you're all familiar with the basic idea of a black hole. By definition, a region of space, strictly speaking not an object, but a region of space from which nothing, not even light, can escape. And the idea of a black hole, even if it wasn't called that, actually goes back quite a long way, perhaps further back than you appreciate. The Reverend John Mitchell, 1783, came up with this expression. I'll paraphrase it. If a sphere of the same density of the sun were to exceed that of the sun in the proportion 500 to 1, all light emitted from such a body would be made to return towards it by its gravity. In other words, if we think of the sun, if we simply make it bigger but keep the same density, then he figured out that simply from the pull of gravity, the light would not be able to escape. So that concept of an object behaving the way we now think black holes behave, that's been around for a long time. Back in the 1800s, the idea of such a so-called dark star was effectively forgotten. Although this was written down back in 1873, it was forgotten for over a century. But then in the early 20th century, we had a number of contributions. I'm not going to talk through all of these. I've just put the key names and dates. If you wish, you can go and look up more information about these people at a later date. But it really kicked off with Einstein with his general theory of relativity back in 100 years ago, 1915, which was then followed up by people taking his theory of gravity, going one step beyond Newton. Einstein was talking about the way mass distorts space and time in ways that we'll see throughout the course of this particular talk. And other people picked up on his equations and applied them to stars or galaxies or the universe. So Schwarzschild and Eddington were talking about what happens if we take Einstein's ideas and apply them to very compact masses. In other words, what if we take a large mass but think about it occupying a very small volume? It was realized at the time that space and objects that are compressed behave very oddly when you get to certain limits of how much you compress a given mass into a given volume. Not only that, it was also realized that not only does mass affect space, it also affects time as well. And in the bottom right-hand corner there, I've given you a little statement that general relativity not only predicts the way that space behaves under the distortion of matter, but it also talks about how time stands still at a particular radius, which we'll come to shortly, which we call the Schwarzschild radius, in honour of Schwarzschild there in his work from 1916. Time stops at a particular radius when we generate a black hole, and hence these objects, although they were called dark stars in the first place, were for a little while called frozen stars because of time standing still. But many decades later, the term black hole caught on, and that's what we've been calling these things ever since. So I've broken the main part of the science fact of this talk into 4 pieces, which I've colour-coded by this jigsaw, just to make it a little easier to tell which section we're dealing with. The first section is going to talk about escape velocity. We're talking about light not being able to escape from a black hole. So to make sure we understand that, we're first going to talk about escape velocity. Then a few words about general relativity. We're not going to go through the maths, you'll be glad to know. And then a little bit about stars and galaxies and how black holes might form. And then we'll finish by thinking about how we can detect gravity of remote objects. And each of these, it doesn't really matter in which order we take them, but we're going to take them in the order I've just presented. We're going to look at each of these pieces in turn, and then once we've understood each of these 4 pieces of the jigsaw, then we'll have a much better holistic understanding of what black holes are. And we'll start by looking at escape velocity. And for the benefit of this talk, and if you want to look at the handout afterwards where each of these slides is laid out, this particular colour coding of the jigsaw will appear in the top left-hand corner of each slide, just to remind you which section we're on, either during this talk, if you do fall asleep and then wake up and realise the colour has changed, or if you're looking through the handouts, it'll just remind you which section we're dealing with. So let's start with escape velocity. The escape velocity of the surface of any body, whether it be the Earth, the Moon, the Sun or a black hole, depends on only two things, and it only depends on the mass and the radius. Strictly, it depends on the ratio of the mass to the radius. That's the only thing that the escape velocity depends on. You might think that sounds a bit odd, because if you pick up an object like a pen here and throw it and you want it to escape from the Earth, you might think it depends on which direction you throw it. What if you throw it directly up? What if you throw it horizontally? Surely that makes a difference. Well, actually no. If you ignore the effects of the atmosphere slowing down an object that you're trying to accelerate, then if you did want an object to leave the Earth's gravitational field, then it doesn't actually matter in which direction you throw it. It only depends on the mass that's generating the gravity to keep that object pinned to the surface, and the distance from the centre of that object, which here we're calling the radius. So m over r. And if we were to calculate the escape velocity for a few bodies, for instance, the escape velocity from the surface of the Moon is 2 kilometres a second. I've written it in old money for those who prefer miles per hour, so about 5,000 miles per hour. The Moon is not very massive, it's small, but it's not very massive, so it has a relatively low escape velocity, making it easy for the Apollo astronauts, for instance, to leave the Moon in their lunar module. The escape velocity from Earth is 11 kilometres per second, or about 25,000 miles an hour. So roughly speaking, that's how fast the Apollo astronauts had to go in order to leave Earth's orbit and head on towards the Moon. If we were to take a larger object like the Sun, much more massive, yes, it's a larger radius, but its mass is much larger, and so the escape velocity from the surface of the Sun is about 600 kilometres per second, or more than 1 million miles an hour. And that might sound like a ridiculously large velocity, but bear in mind that it's only a tiny fraction of the speed of light. It's only 0.2% of the speed of light, which is just as well, because otherwise, of course, the light and the infrared radiation from the Sun would not reach us and keep us warm and keep us lit. Let's ask what happens if we were to take a body, which is the mass of the Sun, so we keep the m in the escape velocity m over r, but what if we make r smaller? If the escape velocity depends on the mass divided by the radius, if we keep the mass the same but make the radius smaller by compressing the object, then what do we find? So here we're going to plot the velocity, the escape velocity vertically in this graph, as a function of the radius of the object we're talking about, in this case the Sun. So there's where the actual radius of the Sun is, and we've just seen that its escape velocity is about 600 kilometres per second. If we take that same mass and make the radius smaller, if we compress the Sun down to 30,000 kilometres, then the escape velocity goes up, because the escape velocity depends on mass divided by radius. And if we make the Sun even smaller, the escape velocity goes up. So when the Sun is only about the size of the Earth, a little bit smaller than the Earth, then the escape velocity would be 10,000 kilometres per second. Make the Sun smaller, the escape velocity goes up. Make the Sun smaller, the escape velocity goes up. And at some critical point, in this case, when we make the Sun's radius only 3 kilometres, what happens? The escape velocity reaches 300,000 kilometres per second. That's the velocity of light. So at that point, the escape velocity from the surface of the Sun would be such that no light would be able to escape. And we talk about that particular radius as the event horizon occurring at a Schwarzschild radius of 3 kilometres. Schwarzschild radius is simply the name we give for the radius needed to generate a black hole. And that surface from which no light can be emitted from inside is called the event horizon. The event horizon isn't physical, it's simply a region of space. In effect, it's a one-way valve. Objects can fall into the black hole, but nothing can come out through the event horizon. So we've just said that we can compress the sun down to 3 kilometers. That would generate an escape velocity higher than the velocity of light, and hence we would form a black hole. But what if we started with a different mass? What, instead of taking the sun, what if we took a different mass? For instance, if we took the Earth, how much would we have to squeeze that in order that the escape velocity reached the velocity of light? Well, we'd have to squeeze the Earth down to far less than 3 kilometers. We'd have to squeeze the Earth down until it was about the size of a marble, about a centimeter or so, a few centimeters in radius. And a smaller object still, the Moon, we would have to compress that down to a radius of a fraction of a millimeter. It would have to be no larger than a grain of sand for the Moon to form a black hole. And we can take this idea further. We can take an object with a mass of Mount Everest, and we can ask, how much do we have to squeeze that? Well, we'd have to compress Mount Everest down to a volume smaller than the volume of an atom before we can generate a black hole out of Mount Everest. Now, of course, we have no idea how we could possibly compress matter to that sort of density, but here we're talking about what would the radius need to be for a given mass in order to generate a black hole, in order to generate escape velocities greater than the speed of light. And those are the numbers. We don't know how to do it, but just because we don't know how to do it doesn't mean it's impossible. If we could compress those objects down to those sizes, we would generate a black hole. A black hole is not something that's only limited to stars. That's what we know about, but in principle, any object could become a black hole. So before we move on to the second piece of the jigsaw, have there been any hands raised yet, Matt?
No. Well, actually, I've got one.
Yep.
Does this have any tie in with dark matter? With missing mass in the Earth?
No, in the sense that it was assumed that dark matter is not easily visible, and perhaps dark matter could be black holes and other objects floating around that we can't readily see. And so a test was done some years ago to actually look for black holes, not look in the sense of look at the light they're producing, but to look for black holes in the sense of the gravity that they produce, and to actually see within our Milky Way if there are enough black holes to account for dark matter. And the answer was no, there aren't. Yes, there's lots of black holes out there, possibly millions of them, but we would need many, many tens or hundreds of billions of black holes in order to account for the missing mass that we call dark matter. So it was considered, but it's been ruled out.
Tiny black holes that may or may not exist.
Tiny black holes would not last very long. They would radiate very quickly and they would evaporate. So it would have to be the larger variety that have been around for long enough to produce the effects that we observe. Okay. If there's nothing else, let's move on to piece 2 of the jigsaw. And as I say, this is not going to be a mathematical treatise. This is just reminding ourselves of what Einstein said. Einstein's general theory of relativity can be written as that. G equals 8 pi t. That is ridiculous oversimplification in that G and T are both very complicated entities in their own right, and a full mathematical treatment is horrendous, well, horrendous to most people except mathematicians, etc. So what it's really telling us is that space, which is represented on the left, is related to matter, which is represented on the right. And most people have a better way of thinking of it rather than writing out the maths. And that is that we can think of space being distorted by mass. So mass tells space how to warp or curve, and space tells mass how to move. Now, the first problem we have is how can empty space be curved, and what do we mean by curved? If we've got a three-dimensional space, what does it curve into? And we all have a problem with that. Mathematicians are quite happy to say, well, here are the equations, this is how it all works. But the rest of us have problems with what do we mean by curved space. And we have to resort to an analogy. We have to say, well, if we were thinking of space as two-dimensional, then we can imagine that two-dimensional space being distorted, like a rubber sheet or something like that. But if we're talking about three-dimensional space, we really could do with a fourth spatial dimension to warp space into, and that, not unnaturally of course, is very difficult to imagine, because our brains are simply not wired that way. Our brains are wired in a way to make sense of the world around us, and that means that we've got used to the idea of three-dimensional space because that is what we can perceive. Mathematicians and some physicists are quite happy to extend that and say, well, I can only see three dimensions, but if we imagine there was a fourth dimension, then I can see how space can be curved or warped or distorted. So it's difficult for most people, but we end up with analogies by thinking about two-dimensional space. If we represent only two dimensions of space and ignore the third, then we allow ourselves the third dimension to allow the distortion. So here, for instance, if there was a flat two-dimensional space, then we place a black hole somewhere near the middle of this sheet. It can distort the sheet, and for large massive objects it'll distort a little bit. For a black hole it distorts into a, as it were, infinitely deep funnel and produce this sort of distortion. So this is the sort of picture that we have in our heads when we talk about how space is warped. We can't really talk about warping three-dimensional space unless we get into the mathematics, which we are definitely not going to do in this particular talk. So we have to accept that this particular artist's impression is precisely that. It's not a true picture of what a black hole looks like, but it does give us the impression of how space is distorted in the environment immediately surrounding a black hole. And that basically has to be good enough if we just want a visual impression. If we're not going to get stuck into the maths, then the best we can do is think about this sort of funnel picture of how space is distorted in the environment of a black hole. We just have to take it on trust that Einstein knew what he was talking about. So why do we trust Einstein? Surely such a crazy idea of general relativity and mass distorting space and time, surely that can't be right. Why do we believe Einstein? Well, we believe Einstein because general relativity, as well as talking about black holes, makes predictions that we can test. For instance, the orbit of Mercury is known to precess. The orbit, as indicated in that little animation on the left-hand side, or the graphic on the right, the orbit of Mercury is not an ellipse which closes on itself. That ellipse slowly, slowly, slowly rotates around such that the closest point of Mercury's orbit to the Sun is in a slightly different position every year. It takes many, many decades, if not centuries, to see a substantial change, but it can be measured, and Newton's theory of gravity was not sufficient to explain why Mercury did that. But when general relativity was applied to the orbit of Mercury, it was found to give the correct observed precession of the Mercury orbit. And therefore, this was one of the crowning glories of general relativity, that managed to predict something correctly that Newton's theory of gravity could not. So that's one reason we believe general relativity, but there are a shed load of others. For instance, when we look at an eclipse, we see stars in the background because the moon is covering the sun's disk. It allows us to see stars that would normally be invisible. But if we imagine those stars being in a position in the sky when the sun is not there, if you imagine that particular chunk of sky, but 6 months on, so that the sun is in a different part of the sky, or if you like, the Earth is in a different part of its orbit, so that that part of the sky is then visible at night rather than visible during the day, we can see where the stars are, and during this eclipse it was noted that the stars shift simply because the starlight is grazing the edge of the sun and being distorted by the gravitational influence of the sun. In other words, the sun is a massive body, and the massive body is distorting space around the sun, and as a result the light actually follows a slight curve rather than a straight line. So that was a prediction again made by general relativity, and in 1919 stars were plotted during this particular solar eclipse, and the amount by which these stars moved was the amount that general relativity predicted. Two independent tests of the theory shortly after 1915, when the general theory of relativity was first published. We have done other tests of general relativity. one of the most bizarre predictions is that time slows down in a gravitational field. In other words, not only does mass distort space or curve space or warp space, but mass also affects time, which is very counterintuitive and very non-Newtonian. But this has been tested. This is why we believe Einstein. For instance, a whole load of atomic clocks were flown on an airliner, second class apparently rather than first class. So these atomic clocks were flown in an aircraft, and they were flown backwards and forwards from east to west and west to east. And not only did the time according to those clocks differ from the time on clocks on the ground, but also we know that the time will be affected from the special theory of relativity. We know that a fast moving clock will record time at a different rate to a slow moving clock. But in addition, there was the effect of the fact that the aircraft was flying a particular height above the Earth, and therefore was a few thousand meters or 10,000 meters or so above the Earth. It was 10,000 meters further away from the center of the Earth, and if time slows down in the gravitational field, that means the clocks that were left on the ground actually ran a little bit slower than the clocks that were in the aircraft. Even after taking special relativity into account because of the speed of the aircraft, there was this effect due to general relativity. So both special and general relativity were checked using these clocks. And not surprisingly, the amount by which the clocks were slow or fast came out to be exactly what was predicted by special relativity and general relativity. So we believe Einstein. Another area that is actually quite an important one is if you think about GPS satellites that are giving us the position of cars on the road or ships at sea or aircraft in flight. The atomic clocks that are on those satellites will go fast or slow depending on how fast those satellites are moving in their orbits and how high those orbits are above the surface of the Earth. The satellites are nominally all at the same height, but they do differ a little bit. And if we did not take special relativity and general relativity into account, then the clocks, the atomic clocks on those satellites, would slowly drift. And it would not be long before, instead of getting accuracy of a few meters for our object on the land or in the air or on the sea, we would find that our positional accuracy would be off by kilometers or tens of kilometers or hundreds of kilometers. So it is important that we understand what is the effect of general relativity, what's the effect of special relativity on these atomic clocks that are in the GPS system. They try and minimize the effect simply by resynchronizing the clocks as often as possible, but it has to be taken into account that there is a drift of the clocks over many days and many weeks. One of the important predictions of general relativity, hereafter simply abbreviated to GR. One of the predictions that's rather important for what we're going to say in a few slides' time is the prediction of gravitational waves. In other words, ripples, just like if we had a mill pond with effectively a flat water surface and then we throw a pebble in there, we generate ripples which spread out from the point of impact. We would expect, if there's a lot of mass moving around, not a star just sitting there on its own, but if one star, for instance, was orbiting another star, or if we had the creation of a black hole, we would expect to find ripples, not in water, but ripples in space itself, strictly speaking, in space-time. And it would be rather tricky to see, but if we could magnify the effect so we can see what's going on, if we had these ripples in space produced by gravitational waves, if they went through a cylinder represented in this middle animation here, then this cylinder would distort in the way shown. A circle, for instance, would distort one way into an ellipse and then the other way, and then into an ellipse and then the other way, backwards and forwards, backwards and forwards. That's characteristic of the passage of a gravitational wave through an object. This animation, as I'm sure you're aware, is grossly exaggerated in the sense that the size of the ripples we're expecting are not going to be a 10% or 20% distortion of the size of this object, as the animation would indicate. It's not going to be a 1% effect, it's not going to be a 1 part in a million, it's not going to be 1 part in a billion. The predicted size of these ripples in space-time are going to be of order 1 part in 10 to the power 20. 1 part in, what is that, 100 million, million. An absolutely tiny effect. So although this was predicted by general relativity 100 years ago, a lot of people have simply ignored that for many decades because it was calculated that the effect would be so small it would be absolutely impossible to measure. More of that later. We're now in a position to move on to the third piece of the jigsaw. Short pause. Matt, any other questions?
One from me, nobody's got the hand up, so unless everybody wants to...
Okay, let's press on then.
Okay.
So let's have a think about how black holes are born. One of the ways you can generate a black hole is by waiting for a really massive star to come to the end of its life. Unlike the sun, very massive stars don't live very long. So our sun, for instance, might live for maybe 10 billion years, but very massive stars use up their fuel very quickly because they're trying to hold against gravity of a very massive star trying to crush the star. And so the fuel is used up very quickly, and in maybe only a few million years, the star can collapse and produce a black hole. If it's massive enough, the star might collapse into a black hole. If the star isn't particularly massive, it might end up as a white dwarf or a neutron star, but we think above a certain limit to the size of a star, they will probably end their life as a black hole, because a supernova will occur. A supernova will effectively eject most of the star off into the void, into the interstellar medium, where it'll enrich the gases to make new stars, but what's left, perhaps 10% of the star, will be left as a black hole if gravity cannot be resisted, if you like. If the mass is large enough, the gravity will crush down and nothing can stop that central region compressing effectively to nothing. So this is simply an artist's impression. It's a bit ridiculous, but when a star goes supernova, the implication is that it could produce a shock wave which cuts a planet in half. Well, actually, when a star goes supernova, the amount of energy released is so enormous, it will completely wipe out any solar system that it's a part of, and probably a few other solar systems as well. So it is a very, very energetic event. But we think we understand the evolution of stars, and hence we understand why the end of the life of a massive star might end up as a supernova with a core that ends up as a black hole. If we do get a black hole, it's bad news for anything that comes close. For instance, if another star happens to get too close to a black hole, there's the black hole on the left. We didn't see it at first because we didn't notice it, but as another star got dangerously close to that first black hole, it got completely disrupted, and you notice that most of the material from that star doesn't simply go down the plug hole, if we think of the artist's impression that we saw before, of the plug hole being a sort of analogy for the black hole. Most of the material actually ends up circling the black hole. Let's just run that video again so we can see it. There's the black hole on the left-hand side, which we can hardly see, but if a star gets too close, its gravity of the black hole can be disrupting the star, and then the material of the star ends up, some of it going down the black hole, but a lot of it ends up circling. It's effectively a queue for all the material that's waiting to go down into the black hole. Like emptying a bath, you can't get all the water down the plug hole at the same time. In this particular case, we see jets coming out. A lot of energy is released in this process, this accretion process. The energy finds it very difficult to get out in the plane of the disk and often comes out as jets in the directions perpendicular to the disk. So the tidal forces, if you get close enough to a black hole, can be huge. And it's sometimes referred to, the disruption of matter is sometimes referred to as either spaghettification or the noodle effect. It's not often astrophysicists use terms like that, but these are used to give us a good indication of how matter is disrupted if you get close enough to a black hole, simply because of the very strong tidal effects that would be there. Let's have a look at what's going on in the centre of our own Milky Way galaxy. The centre of the Milky Way is somewhere around here, and we're zooming into it a little bit at a time, from an original camera picture to a telescope picture, and then we're switching to a different telescope with higher resolution, and then we're still zooming in, and then we're switching to another telescope with higher resolution, and we're zooming in again. So we are zooming in right to the heart of the galaxy. And what we find is a few stars. They look a little bit indistinct, but remember how much we've zoomed in here. If we take each of these blobs as being the position of a star and reduce the star just to its central point to make it a little bit clearer, we find that the stars aren't just randomly moving around in the center of the galaxy. They all seem to be behaving like they're orbiting one object which we can't see. There doesn't appear to be any visible object at the core. Let's just have a slightly different look at how those stars can be represented. So here's just a few of those stars. Over a period of a few years, the star positions have been plotted, and notice, for instance, this star here. If it's observed over a few years, what we see is that this star moves towards a point where the ring there indicates that there's a very massive object. It must be massive to take a star and whip it round like that, but there appears to be nothing in that position which is actually shining. There appears to be no light coming out of this region, but it must be massive in order to make the stars move the way they do. Over a period of a few years, it must be a very massive object. And using our knowledge of gravity, we can calculate how massive must that object be in order to make the stars move that way. So we call this a supermassive black hole because this particular object, which is very massive and doesn't seem to emit any light, and so we take it that this must be a black hole, we can calculate its mass, and it turns out to be much greater than the mass of simply one dead star. For instance, we've said that massive stars might end up as a supernova, and the core of that star might end up as a black hole. But the black hole we're talking about at the center of the Milky Way is very much larger. Looking at the way those stars are moving, we calculate that the so-called supermassive black hole, hereafter SMBH, the supermassive black hole at the center of our Milky Way galaxy, appears to have a mass of 4 million solar masses. This symbol on the right, M with this circle dot, is simply shorthand for the mass of our Sun. It's a bit crazy to start putting masses in kilograms, so we're going to talk about the mass of an object in terms of how massive is it compared to the mass of our Sun. And remember from what we did in the first piece of the jigsaw, we know how escape velocity depends on mass and radius, so we can work out the physical size of the event horizon of this particular black hole. If we know it has a mass of 4 million solar masses, then we can work out how physically large this object must be. Let's just start with the scale of the solar system, just to give us some reference, as it were. Let's just grey that out a little bit so it's not quite so bright. If we work out how large this black hole is, which is 4 million solar masses, it turns out to be that size. We've just plonked it down there. It's bigger than the Sun, but substantially smaller than the orbit of Mercury. That just gives us a reference there. The black hole at the centre of our Milky Way galaxy is nothing special. It appears that there's black holes at the centre of lots of galaxies that are observed. We're not quite sure yet if every galaxy has a black hole at the centre, but it would appear that quite a lot of them do. And when we look at other galaxies, we find even more massive black holes. For instance, other SMBH, other supermassive black holes, are larger than the one we have in the Milky Way. The one in the Andromeda galaxy is 250 million solar masses in mass. And again, if we convert that using our equation for escape velocity, we can work out how large that particular black hole is. And it turns out to be about the size of the orbit of Jupiter. Not the size of Jupiter, the size of the orbit of Jupiter in our solar system, just to give you an idea of scale. That is not the largest either. If we look at the Sombrero galaxy, M104, then we find the supermassive black hole at the heart of that galaxy appears to be 1 billion solar masses. So again, if we work out its size and put it on the same scale, we find out that black hole would be larger than the orbit of Uranus and nearly the size of the orbit of Neptune. I'm not sure what the record holder is at the moment, but last time I checked, one of the largest black holes that was known has a mass of more than 20 billion solar masses, and it's too large to fit on this diagram, so there's a little bit of it in the corner there. You get an idea that it is substantially larger than the orbit of Pluto and would occupy a fair large chunk of the Kuiper belt or the Oort cloud. So these supermassive black holes, we know they exist, we can detect them in the centre of our Milky Way, and we can detect their presence in the centres of other large galaxies. So I think this is the point where I said we would take a short break. I've covered 3 pieces of the jigsaw, and the remaining part, the detecting gravity piece of the jigsaw, will be followed by a little bit about the science fiction and the future. So I'll just hold here for the time being. Okay, welcome back from your well-deserved tea break. So now we're going to go on to the 4th piece of this jigsaw, having covered escape velocity and general relativity and having a quick look at stars and galaxies for the existence of black holes. Now let's think about how we might detect their existence. So I'm not going to cover everything because time is against us in the long term, but I'm mainly going to talk about something that I mentioned a few slides back, and that is that general relativity predicted the existence of gravitational waves. And even though many people said they are going to be way too small, the effects that we're looking for, the distortions of space, the ripples in space that we can expect to see from a very dramatic event such as, well, one black hole crashing into another, it's very unlikely that we'll ever have the sensitivity of any device on Earth to see those ripples in space-time. If they're only 1 part in 10 to the power 20, how on Earth can we ever hope to measure them? That didn't put some people off. They said, well, let's build an interferometer anyway. So what they did is build a couple of interferometers. I'll explain what those are in just a second. One interferometer was built in Hanford, up there in Washington, and another one was built in Louisiana, in Livingston. And these are large L-shaped interferometers. You can see the L here. There's a very long, what appears to be a pipeline there going into this building, and at 90 degrees another pipeline going off into the distance. The 2 arms of these interferometers are both about 4 kilometers long, and together they make up LIGO, the Laser Interferometer Gravitational Wave Observatory. And the idea is that if gravitational waves are passing through the Earth, then it might be possible to detect them if we send a laser beam up these 2 pipes. The laser beam will take the same length of time to go up and hit a mirror and come back again if these 2 arms are the same length. But if a gravitational wave is passing through, as we saw in that animation earlier, then for a fraction of a second, remember the distortion of the circle becoming an oval one way and then an oval the other, as this gravitational wave passes through the Earth, then for a small fraction of a second, one arm will become a little bit longer and the other arm will become a little bit shorter. So if we send laser beams out along both arms, hit a mirror and come back again, then the length of time it takes to go out and back will be slightly different if the arm is longer compared to if the arm is shorter. And if, I'm not sure I can do this on Zoom, but if we imagine a gravitational wave passing through, what's going to happen is one arm is long, one arm is short, and then it'll be the other way round, then it'll be back again, then it'll be back again, then it'll be back again. So if we can time very accurately how long it takes these lasers to go out and back, then we might be able to see the effects of gravitational waves passing through the Earth. That was the idea. The mirrors at the end of these 2 4-kilometer arms are these huge lumps of glass here, suspended in a sort of a pendulum. That's rather important because we don't want to take this mirror and bolt it into a frame which is then bolted into the ground, because what would then happen is the mirror would vibrate as the ground vibrates, whether it be somebody slamming a door or a train going by 10 miles away or a little bit of an earthquake, for instance. These mirrors would always be vibrating. So the intention was to try and make these things as decoupled as possible from the surrounding Earth, the body of the Earth, and to try and make them independent of any man-made interference as possible. So the idea was the light would be sent down these long arms, bounce off the mirrors. Actually, it would bounce backwards and forwards quite a few times. So although it's a 4-kilometre arm, the light would actually travel many tens of kilometres, if not, is it hundreds, thousands of kilometres. It would bounce backwards and forwards a large number of times before being measured. How can you tell if one light beam is slightly out of phase with another light beam? Because remember, these distances are almost the same. There are tiny changes. Well, it would need a very sensitive interferometer. An interferometer looks at the interference between light going on one path and light going on the other path. I'm not going to tell you how this very complex beastie works. Let's just take it as read that if there was a slight difference in those two arms, this interferometer hopefully would be capable of measuring it. And what happened? Well, in February of 2016, it was announced that they had successfully measured a gravitational wave passing through the Earth. What they thought it was is indicated by this artist's impression in the background, two black holes merging. And the trace at the bottom there shows you the trace from the two interferometers. One of the reasons that there are two interferometers is nobody was going to believe the result unless the two interferometers independently both measured effectively the same signal within a fraction of a second of each other. And if we separate out the data, we can see what the Hanford interferometer actually picked up. So the top one shows you, it looks a little bit like noise. And then it seems to be, there's a particular pattern in there, getting larger and larger and larger and larger and then disappearing. This vertical axis here is strain, the amount by which the distance between the mirrors appears to have changed. So you can think of that as meaning, how much has 1 meter changed? Has it changed by 1 millimeter or 1 micron or 1 nanometer? It's changed by 1 part in 10 to the, roughly speaking, 21 in this particular example. And the horizontal axis here is time. And if you look at the bottom, you can see it's just a fraction of a second. Over a few tenths of a second, the signal in the Hanford interferometer seemed to change from noise to a particular signal which had a particular characteristic of a growing amplitude and an increasing frequency. You see these peaks and troughs are not only getting higher, they're getting closer together in time until the whole thing has finished. That would be unbelievable if it wasn't for the fact that the Livingston interferometer effectively gave the same trace at the same time. Effectively noise for the first fraction of a second, and then it showed an increasing amplitude of signal, getting larger and larger in amplitude, higher and higher in frequency, and then dies away to nothing. And if we superimpose those two on top of each other, as you can see in the bottom here, we can see that apart from a little bit of noise on the left and noise on the right, they seem to be showing the same variation. In this particular case, the data is the rather thicker line, and this thin line you can see here is the prediction, or if you like, a model of what we think would be expected based on what we think happened. What we can't do is take the data and simply say, well, from that we can determine what it is that actually produced these ripples in space. What the theorists have to do is to say, well, let's think about what might have caused this particular event. Let's say two black holes colliding with each other. Let's test lots of ideas. What if the first one was this mass and the second one was this mass and they collided? What would we expect to see? And what the theorists have done is gone through lots and lots and lots of different scenarios of possibilities and then tried to match up all one of those as being the best match to the data. And the best match they could find is this thin line, which I hope you can see okay, which is a pretty good match to the actual experimental data, both in the case of the Hanford interferometer in yellow and in the Livingston interferometer in blue here. The story that this data is telling us is quite incredible. The fact that it worked at all is pretty amazing. The fact that it is possible to build an interferometer that can see variations in the ripples in space, which are only a few parts in 10 to the 21. The fact that it's technically possible is absolutely amazing. But the story of what produced these ripples is almost equally amazing. because it was found that the only way you can predict that this is what you would expect to get from Einstein's theory of relativity, the only way you can get this particular pattern, this particular fingerprint, if you want to think of it that way, is if the following happened. About 1.5 billion light years away, two black holes were orbiting each other and getting closer and closer and closer together. And at some point they merged to produce one black hole. One of these black holes had a mass of 29 solar masses. 29. The other black hole had a mass of 36 solar masses. 29 and 36. These two black holes merged together and produced one big black hole of 62 solar masses. Anybody that's still awake at this point will realise that 29 plus 36 doesn't equal 62. 29 plus 36 equals 65. So this black hole that was made is 3 solar masses lighter than you would expect if you just took these black holes and placed them together. So where did these 3 solar masses go? Well, these 3 solar masses were converted from mass into energy. Let's get an idea of the scale of that. The energy is then carried away by the gravitational waves. Let's get the scale of that. Our sun has a mass of 1 solar mass, and it's converting a small amount of that into energy, and it has been doing for 5 billion years or so. By the time it gets to the end of its life, in another 5 billion years, it will be a 10 billion year old star, and during that time it would have used a very small fraction of its fuel. In other words, the sun at the end of its life will have a mass which is at least 99% of its original mass. Only a tiny fraction, barely 0.5% of its mass will have been converted into energy during its 10 billion year lifetime. What's happened here with this black hole merger is that 3 solar masses have been converted into energy in their entirety. 3 entire solar masses have been converted into energy. Our sun will convert 0.5% of its mass into energy, and it will have done so over a period of 10 billion years. This particular event converted 3 solar masses, so effectively 300 times as much, but instead of doing it over a time period of 10 billion years, it's done it in about 1/10 of a second. So the energy released in that instant was absolutely vast. It must have been, otherwise we couldn't possibly have seen the ripples in space over a distance of more than 1 billion light years. It's been estimated that the energy released in that event was not like a supernova, for instance, which can outshine all the stars in its galaxy. This particular event was so energetic, the merger of these black holes was so energetic, it released more energy in that instant than not only all the stars in its galaxy, it released more energy than all the stars in all the galaxies in the observable universe for that fraction of a second. That's how amazing that particular event was. That was discovered, it was announced in 2016, the data was actually taken in 2015, and that was when it was released, Astronomy Picture of the Day, 11th of February 2016, and perhaps you saw a few days ago the Astronomy Picture of the Day on the September the 8th was another event detected by LIGO, in this case even more massive black holes, not 29 and 36, the black holes that merged to produce the ripples in space that they've announced just a few days ago. These were even larger. Instead of 20-ish and 30-ish, they were 60-ish and 80-ish solar masses merging into a monster of a black hole of about 140 solar masses. By no means as large as the supermassive black holes at the centre of our galaxy, but still very large for the sort of black holes that we thought could exist at the end of a star's life. So the LIGO story is amazing as a piece of perseverance It's amazing that people actually got the funding for an idea to measure something that most people thought would never be possible to measure. The fact that they got the money, the fact that they built these interferometers, the fact that they got them to work through an international collaboration of many countries in the world putting in expertise and many decades of blood, sweat and tears to actually get to the point where they can measure these ripples in space-time produced by these black holes. Now that LIGO has shown that it's possible to measure gravitational waves, now the next step is to say, well, okay, let's build more interferometers like LIGO. Only having 2 interferometers in America is rather limiting. If we had a few more around the world, then not only would the sensitivity go up to see lesser and lesser energetic events, but also it would mean that they could triangulate and get an idea of where this event was. The first one that I mentioned, these black hole mergers, they really couldn't pin down where it was that this particular event took place. They knew it was very distant, 1.5 billion light years away from the intensity that they could measure, but they didn't really know which galaxy this occurred in. All they knew it was sort of on the left-hand side of the universe. That's really all they could say. More interferometers will mean that you can then start pinning down, this particular event occurred in that galaxy. Let's go and have a look at that galaxy and see if anything interesting is going on there. Maybe there's some light or some X-rays or some gamma rays or some radio waves that are also being radiated by this particular event, which we've just seen through our interferometer. And if it works with interferometers on Earth, then it's now being planned, nothing yet, but it's being planned. Why don't we build interferometers in space? Why limit ourselves to having an arm which is 4 kilometers to bounce the laser backwards and forwards? Why not put the lasers in space and then the arms can be millions of kilometers long? So there are plans now to put satellites, as indicated by this little schematic here. You put satellites with lasers and you bounce the lasers backwards and forwards between the satellites. You need to have exceptional station keeping to make sure you know where those satellites are so that you can monitor how the laser beams are changing in terms of their distance between the satellites. And you have to do an experiment over a long period of time to take out a lot of experimental errors that would otherwise confuse the experiment. Why would you want a much longer arm? Well, one of the reasons you'd want a longer arm is then you can measure ripples in space-time that are much longer, so-called wavelengths, the distance from the peak to the trough to the peak. You can measure ripples that are much longer in wavelength and more slowly evolving rather than the rather rapid ones that have been seen by interferometers on Earth. So LIGO, for instance, is sensitive to changes with a time scale of a fraction of a second. That means it can detect black holes crashing into each other or merging neutron stars, for instance. But maybe that doesn't happen very often. With ELISA, with a much larger arm for our interferometer, it would be sensitive to much longer periods, longer wavelengths, longer periods of things happening over periods of seconds or hours or days. That means that if we had this so-called evolved laser interferometer space antenna, big name, but the acronym is nice and easy, ELISA, it means that ELISA could detect black holes from within our galaxy and possibly supermassive black holes from galaxies beyond our own Milky Way. It might also be possible that ELISA, if it ever gets built in the next decade or two, it might be able to detect the gravitational waves which came from one of the biggest singularities of all, the Big Bang. At the moment, when we look back as far as we can with telescopes looking at light or microwaves or radio waves, with electromagnetic radiation, we can only go back so far, not all the way to the Big Bang, but we can only go back to within about 500,000 years of the Big Bang. With gravitational waves, we might be able to see all the way back to time zero. So that could be an enormous advance that we get if and when ELISA gets built. Perhaps you've heard of other ideas for measuring black holes, not only things like LIGO, which is sensitive to colliding black holes, but perhaps you've heard about the Event Horizon Telescope, linking together radio telescopes around the world to make effectively a radio telescope with a dish whose resolution is equivalent to a dish the size of the Earth. That produced this image of a black hole at the centre of a galaxy called Messier 87. So M87 star is the name given for the supermassive black hole at the centre of this particular galaxy. It's tempting to say we're looking at the black hole there as the dark patch in the middle. Strictly speaking, the dark patch in the middle is a sort of shadow produced by the fact that the matter that's trying to fall into the black hole, this so-called accretion disk which we mentioned earlier, the matter is getting very hot as it tries to go into the black hole, and that's producing a sort of pancake or something like Saturn's rings around the black hole. And the black hole itself is producing a shadow, stopping us seeing all of that accretion disk. Perhaps the best way of visualizing what it actually should look like is to look at a little animation that came up in the astronomy picture of the day. This is what it looks like from above. That's the accretion disk seen from above. And we're spinning to see the accretion disk from the side, and now we're seeing the accretion disk from underneath. But although this thing should look a little bit like Saturn's rings, because the accretion disk is effectively just a flat pancake, what we can see is the left and the right look sort of sensible, but at the back we shouldn't be able to see this because it's, as it were, hidden behind the black hole. But the gravity of the black hole is so strong it's bending the light from the part of the accretion disk behind the black hole, and the light is coming over the top. And similarly, the underneath of the ring in the background is visible as well for the same reason. The light from the underneath of the ring is being bent by the enormous gravity of the black hole, and that allows us to see the top and bottom of the ring in the background at the same time. And hence you can perhaps now appreciate that what's actually going on in the middle is a shadow region produced by the fact that light from other parts of the accretion disk are eventually making its way to us, but not directly from the black hole itself. And that's why we see something that looks a little bit like that. It doesn't mean that we're looking at the accretion disk face on, because it would look very similar even if the accretion disk was at quite an angle, because of the enormous gravity of the black hole distorting the way the light actually reaches us. So we've looked at the facts. We've looked at escape velocity, general relativity, stars and galaxies, and we've had a think about how we can detect gravity, either by looking at interferometry of gravitational waves, telling us how space is being distorted by those masses, and we can also have a direct look at black holes, or at least the accretion disk around black holes, by using telescopes such as the Event Horizon Telescope. Let's just spend a few minutes asking ourselves that, well, if we think we've got the facts right, what does science fiction have to say about black holes? And does Hollywood ever get it right? Or are we assuming that, in fact, there are a few misconceptions out there? Let's have a look at 3 Hollywood films. One, oldie but goldie, The Black Hole. Perhaps you remember that, maybe you don't. Ernest Borgnine, Maximilian Schell. Yeah, no, depends on your age, I guess. A more recent one, Lost in Space, a reboot of the 1960s series. And a sort of sci-fi come horror film, Event Horizon. Let's just have a think about what these particular ones are saying. In The Black Hole, the first picture, a ship is parked right at the event horizon. Because we know that time stands still at the event horizon, that's essentially a fact as far as we know. So the idea was a ship goes up to the event horizon, puts on the handbrake, and just sits there. Because time stands still, you can go and observe the black hole and make all the observations you like about what's going on, and everything is hunky-dory because time stands still, and therefore you're not going to get sucked in. That's the premise of the black hole. In Lost in Space, the premise is, at the end of the film, they are trying to escape from a planet, and as they are getting away from the planet, everything seems to be hunky-dory. The ship appears to be pulling away from the planet, but just at the last minute, the planet collapses into a black hole. Let's not worry about why it does that. Let's just assume that, yep, okay, for some reason, the planet has decided to collapse into a black hole. And as a consequence, the ship then gets sucked back into the black hole, and they have a problem. In the third film, we have a ship which is powered by a black hole. So a black hole actually forms the power source of a particular starship. So at this point, I normally ask for a show of hands, which is probably a bit too tricky at this particular point, but I'll just give you a few seconds to think. 2 of these scenarios are absolute rubbish, and 1 scenario is absolutely plausible. I'll just give you a few seconds to think which you think is the plausible one and which are the bad science alternatives. Okay, time's up. The black hole. Yes, right. Time stands still at the event horizon. Yes, but that does not mean that you can go up to the event horizon, put on the parking brake, and sit there and have a cup of tea watching this black hole. Time slows down as you approach the black hole. Time, as measured by anybody watching you fall into the black hole. As far as you're concerned, time appears to be behaving just the same way as it always does. But as you get closer and closer to the black hole, somebody from a distance gets the impression that you are approaching the black hole more and more and more slowly. But if you ever tried this in a ship, you would just go straight through the event horizon and get sucked in, and who knows what would happen next, because there's no way we can get information out of the black hole to find out what happened to you. But it is a complete fallacy that you can simply go up to an event horizon, stop there, and watch time stand still. It doesn't work that way. What about the ship trying to leave a planet and the planet collapses into a black hole? This is a misconception based on the fact that people think that black holes suck in everything around them. Well, a black hole has a certain amount of gravity based on its mass. If you rearrange that mass slightly, you don't change the gravitational pull. For instance, if the Earth is going around the Sun, okay, yes, the Earth is going around the Sun, if the Sun were to collapse into a black hole, the same mass would be at that particular point, and the same distance from the Earth to the Sun would exist. It would still be the same distance, the same 150 million kilometers from the Earth to the Sun, if the Sun decided to collapse into a black hole. So the Earth would orbit in pretty much the same way as it always did. Yes, there would be no light coming from the Sun. We would notice that after a few minutes, and it would be bad news for us. But it does not mean that the Earth would magically be pulled into that black hole because gravity suddenly becomes stronger. No. When you collapse a given mass into a black hole, that same mass apparently is still there, and therefore you get the same gravitational pull from a given distance. So just because the planet decided to become a black hole does not mean that the ship would suddenly be pulled backwards and then our heroes would then have a problem. So congratulations for those of you who chose the third one. It is entirely reasonable to have a ship powered by a black hole. Reasonable in the sense that it does not disobey any laws of physics that we understand. Is it possible to have a black hole powered star drive? Well, no problem at all. If your black hole is too small, for instance, if you started with a black hole with, for instance, a mass of a kilogram, then you haven't got much energy to work with. You're never going to get more energy than E equals mc squared out of it. So if you start with a kilogram, you're limiting how much energy you can possibly get out of that black hole. If you had a black hole with a mass of, let's say, more than Mount Everest, a few billion tons, then the radiation is quite weak. I haven't talked about radiation. It's in the handout if you want to go and read a little bit about it. But every black hole will radiate. That doesn't mean that things are coming out of the black hole from inside. What it means is, on the surface of the black hole, just outside the event horizon, Stephen Hawking has postulated that there will be radiation for reasons that I'm not going to go into. It's a quantum mechanical phenomenon. But it is thought that black holes will radiate from just outside their event horizon. Large black holes won't radiate much, so supermassive black holes will last for ages, but small black holes will radiate so intensely that they will evaporate after a short length of time. So if it's a really large black hole, the Hawking radiation is very weak. But if you have something in between, let's say a kilogram and the mass of Mount Everest, let's just choose arbitrarily a black hole with a mass of 1,000,000 tons, let's say, then the power in the radiation would be equivalent to, well, it would be equivalent to something like 100 million nuclear power stations at your disposal. Now, 100 million nuclear power stations is a lot of power. And if you want to push an object, okay, it might be quite a heavy object, but if you wanted to push that object at a substantial speed, then having the energy equivalent of 100 million nuclear power stations would be a quite nice power source. Not only that, but your black hole would actually last for quite a while. Although you've got this enormous amount of power at your fingertips, the fuel, if you like, if you want to think of it that way, the source of your energy would last quite a while. The black hole would last for something of order 100 years. So you can quite happily go zipping around between star systems and you wouldn't have to replace your black hole until something of order a few decades later. Pull into a gas station, replace your black hole, and off you go again. Quite how you would do it, I don't know. You would need to make sure your black hole didn't touch the walls. You would need to place it in your engine room somehow. But they figured out how to do it in Star Trek with the warp drives and matter and antimatter. I'm sure you can figure out how to keep a black hole in one place. And the Hawking radiation, you simply shield it on one side and allow the radiation to fly off on the other side. And there you've got your rocket engine that will accelerate you at very high speeds. So there's nothing in that particular scenario that goes against the laws of physics. So if you can make yourself a small enough black hole, 1 million tons would do it. It'll end up, of course, tiny. Its physical size would be much less than the size of an atom. So your engine room can be pretty small as well. And that will give you enough energy to power a starship. What about the idea that if you distort space in the right way, we're back to our two-dimensional analogy of imagining space to be a flat sheet. What if you then distorted it in this sort of way? Is it possible to distort space in such a way that you can take a shortcut from one part of space to another part of space? These are, in science fiction, these are called wormholes or hyperspace or lots of other names for them. Well, is it possible to make a wormhole? Well, it must be, because we've seen it in Stargate and Contact and Star Wars and Star Trek. I mean, this is a staple of science fiction, so presumably it must be possible, or else they wouldn't have said these things. Again, there's nothing in the laws of physics that stop you making a wormhole that gives you a shortcut from one part of space to another part of space. It's only a question of figuring out what mass and energy you need and where do you place them in order to distort space in that particular way. So there's no particular objection to making a wormhole. We don't know how to do it, but that's not the same as saying it's not allowed by the laws of physics. What about time travel? Well, that sort of falls into the same category, that if you distort space, well, actually you're distorting space-time. You can't really separate space and time. I haven't gone into that in detail, but in general relativity, space-time is considered as effectively one entity. So if you can distort space by the right combination of matter and energy and make a wormhole, in principle, you could do the same. And instead of going from one point in space to another point in space, you can go from one point in time to another point in time. And again, there's plenty of ideas right back to H.G. Wells, whether it be the modern version or the version that looks like Elton John would have gone through the Everglades in on the left-hand side. Maybe some of you remember that. And again, there's plenty of other time travel Hollywood fiction and indeed good old UK stuff as well. So what's the problem with time travel? Well, I'm sure you're aware of the paradox of if you go back in time and kill your grandfather, we have a problem. So if it's not disallowed by the laws of physics, how can you square up with the fact that, as far as we know, time travel doesn't exist, other than in fiction? Well, Stephen Hawking had something to say about that. He didn't have a proof, he had a conjecture. And a conjecture is just, this is my idea, if you like. Hawking proposed the chronology protection conjecture. Wonderful name for simply saying, well, as far as we can tell, if you allowed time travel, there would be a real problem. So although physics doesn't stop you doing time travel in the sense that there's nothing there that forbids it, Hawking proposed that a wormhole that allows time travel will collapse before anything has time to go through the wormhole and actually change the past, as it were. So he had no proof of that. He just thought that was a way of protecting time. And basically the phrase that we can use is making the universe safe for historians. It might be that that's the case, that time travel is not forbidden, but practically it cannot be done, and therefore time cannot be changed. You can't change history. That is, as its name implies, pure conjecture. Let me finish with a problem. And the problem is that we know general relativity works really well for massive objects, whether they be stars, black holes, galaxies, the universe. General relativity is great for massive objects. What I haven't talked about is how wonderful quantum mechanics is, which is a really great theory for talking about how tiny objects work, like molecules, atoms, viruses, anything smaller than that, fundamental particles. But of course, when we're talking about a black hole, it's very massive, but if it's compressed down to, well, possibly nothing, as far as we know, once a black hole forms, nothing stops it collapsing. It doesn't end up as 3 kilometers if you take the sun and collapse it. It just keeps on collapsing down to nothing, as far as we know. So if general relativity works really well for massive objects and quantum mechanics works really well for tiny objects, both of these theories have existed for 100 years, and we have not yet found anything which has proved either of them to be wrong. But what if the object, like a black hole, is massive and tiny? Well, then you would argue we need both theories. Of course, we can say, right, we just need to combine them together. We need quantum gravity, that'll do. We just need to put quantum mechanics in bed with gravity, and then we're golden. Then we've got a solution. The problem is, no one has figured out a way of making general relativity and quantum mechanics work together. In other words, they are two quite different theories, and no one has figured out how to make a theory which incorporates both of them. A universal theory of everything is what you really want, and it has proven to be elusive. Even Einstein had problems with the theory of everything. So it is possible that quantum mechanics will stop a singularity from forming. At the moment, we believe black holes end up as zero-sized objects. Whatever the material falls into them, we don't believe the result has any physical size. But maybe that's wrong. Maybe quantum mechanics will prevent a so-called singularity from forming, and then we won't have infinite densities and infinitely warped space. Some theorists are working on string theory, for instance, in which we don't have 3 dimensions of space and 1 of time. We have 10 or 11 dimensions of a universe. And there the fundamental building blocks are not the particles that we're familiar with, electrons or quarks or other particles. There the fundamental building blocks are strings rather than particles. And in that case, black holes would not be a point-like object with infinite density. They would be fuzzballs or balls of string, if you like, and you get rid of the problem of a singularity. But the problem is the universe described by string theory, is that actually the one we live in, or is our universe different from the universe set up in string theorists' heads? And at the moment, we don't know what the answer is. Einstein, as I said a moment ago, had a problem. He never really believed that quantum mechanics was a suitable description of the microscopic world. And he spent a lot of his years wrestling with this idea of how to get quantum mechanics, or something equivalent to it, to work with general relativity, to deal with the very large, the very massive, as well as the very small. He spent years working on the theory of everything, and it ended up turning a rather handsome young man that we see there into the more familiar image we have of Einstein as an older man. If a genius like Einstein couldn't get his head around the problem, what will it take to get a theory of everything which explains the entire universe, including black holes? Well, maybe some unexpected discoveries. It could come from LIGO, it could come from ELIZA, it could come from somewhere else. Maybe they will point the way for a better understanding of black holes. Thank you all very much for your attention.